Good morning, everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this class, we'll talk about solution for elastic critical moment using energy method. In the previous class, we discussed about laterally unsupported beams. As you can see here, it has three different deformations, B, U, and gamma, and it is governed by stability. So the elastic critical moment, MCR, is given as beta sub B into F critical B into Z sub P. And this is a differential equation. And this differential equation is a function of lateral displacement U, vertical displacement V, and the twist gamma. So the corresponding differential equations are shown in the slide. And when we solve these differential equations, we get M critical. So that is also given in the slide on the right hand side. M naught critical equal to pi square EIY divided by L square into root of IW by IY plus GJL square divided by pi square EIY. And this is for a simply supported beam whose ends are torsionally restrained, which is gamma equal to 0. And the n moments are of equal magnitude M naught. This can also be morphed into another simplified equation based on the properties shown here, both material as well as geometric. And this is similar to the equation that is shown on the right hand side, page number 54 of IS 800. And this is very specific to standard steel I sections, doubly symmetric. And the above equation is based on approximate values of G, IY, IW, and J. And the MCR is specific to prismatic members of doubly symmetric standard rolled I sections and welded doubly symmetric I sections. This can be further simplified to get FCRB. Here the simplifications are by substituting IY equal to ARY square and Z sub P equal to A into H by 2. So comparing with M naught CR equal to FCRB into ZE, and this is done by substituting Z sub P divided by Z sub E, which is the shape factor, and for I sections it is 1.1. So limitations of the previously derived solution for MCR. This MCR is only for externally applied moment, which is M naught on both sides, and the beam is simply supported at the ends, which means that twisting is prevented at the supports. The lateral bending or warping is allowed, and the section is prismatic and doubly symmetric cross sections. As you can see here, for I sections or boxed sections. In practice, beams vary from the basic case. Different types of loading are there, unequal end moments and equal end moments acting in the same direction, or a concentrated load or a uniformly distributed load. The loading conditions can be load applied at the shear center, which is a normal condition, or the load applied at the top, which is a destabilizing condition, or the load applied at the bottom of the flange, which is a restoring force, also classified as a normal condition. Now, how do we solve for MCR for different loading conditions? In practice, beams are subjected to a variety of loading conditions. So when it is subjected to the loading that is shown here, MA on the left hand side and MB on the right hand side, producing a single curvature. And when MA equal MB, we see the bending moment diagram on the right hand side. And when MA not equal to MB and MA greater than 0 and MB greater than 0 and MA greater than MB, we have another type of bending moment diagram, as you can see on the right hand side. And for moments acting in opposite directions, it produces double curvature. And you can see that MA not equal to MB, MA greater than 0 and MB less than 0, and MA is greater than MB. We have the bending moment diagram, as you can see on the right hand side. When it is subjected to a concentrated load at midspan, you have another type of bending moment diagram, again shown on the right hand side. So the first bending moment diagram we have solved is a homogeneous linear. It is a homogeneous linear ordinary differential equation with constant coefficient, where M naught is a constant value, as you can see on the right hand side. And this leads to M naught critical value, that is pi by L the whole square into EIY into root of IW by IY plus GJL square divided by pi square EIY, which we have solved in the previous class as well. Now for homogeneous linear ordinary differential equation with variable loads, that is the load which is a variable along the length Z. So here the load P is variable along the length Z. So obtaining equilibrium equation using differential equation is cumbersome, and energy method can be used to form the equilibrium equations. So now let's talk about the total potential energy of the beam. The total potential energy pi of the beam, principle of stational potential energy, is equal to delta pi equal to 0. It states that if an elastic system acted on by conservative forces is in equilibrium, the total potential energy of the system must be stationary. So for equilibrium, the total potential energy of the system pi should be equal to 0, or delta pi is equal to 0. Further, a stationary value corresponds to a minimum or maximum value of total potential energy pi. Minimum value indicates that the equilibrium is stable, which means that del square pi greater than 0. The maximum value indicates that the equilibrium is unstable, which is del square pi is less than 0. So what is the physical significance of the above conditions? The stable equilibrium means that the curvature is positive, which is del square pi greater than 0. The unstable equilibrium means that the curvature del square pi is less than 0. And for neutral equilibrium, del pi is equal to 0. Let us derive the total potential energy equation pi of the beam, which is equal to pi equal to u plus v. Here u is the strain energy of the beam due to internal stresses and strains, and v is the potential energy of the beam due to external loads. So the total potential energy pi of the beam equal to u plus v. So now to evaluate the strain energy of the beam, we need to consider a simply supported beam with a rectangular cross section xyz as the fixed coordinate system in the undeformed position, as you can see from the right hand side of the picture. Under the action of external equal end moment m0 about x-axis at shear center, the member undergoes lateral torsional buckling as shown in figure. The assumptions of linear elastic behavior, small deformations, and no distortion in member cross-sectional shape during buckling still apply. Now, each cross-section in deformed configuration can be defined by three displacement coordinates, that is u, v, and gamma, with x dash, y dash, z dash as the local coordinate system. Strain energy is stored in the beam due to these three displacement components are strain energy of the beam due to bending about x dash axis, due to bending about y dash axis, due to twisting about z dash axis. Obtaining the three components of the strain energy u, consider a cross-section of beam at a distance z1. Now, let us derive strain energy u for the beam from the deformation of infinitesimal element. As you can see, the infinitesimal element is between distance z and z dash. So you can see that mx dash, mo dash, and y dash on the right hand side based on the sign convention, and on the left hand side it is based on equilibrium. So deformation in each plane, in plane bending yz is given here as d theta x dash, and the applied moment is mx dash. Out of plane bending xz plane, here it is dy dash due to moment my dash. Now twisting xy plane due to moment mz. Strain energy due to in plane bending ub x dash. The increment of external work dw external performed as a result of in plane bending is given as half into mx dash into dx dash. Let us introduce the variable v using the following equations. From moment curvature relationship, mx dash equal to eix into d square v by dz square, because due to the moment mx, there is a vertical movement of the beam which is in the y direction. Hence, we have eix into d square v by dz square. Hence, we have mx dash equal to eix into d square v by dz square. From slope curvature relationship, we have dx dash divided by dz is equal to d square v by dz square. Here, theta represents the slope and d by dz of theta x dash represents the curvature. So, d theta x dash is equal to d square v by dz square into dz. Substituting the terms in dw external, we have dw external is equal to half into mx dash into dx dash, which is equal to half into eax into d square v by dz square into d square v by dz square into dz. So, this can be written as half into eax into d square v by dz square the whole square into dz. The increment of external work dw external performed as a result of out of plane bending is given as dw external is equal to half into my dash into d theta y dash. Let us introduce the variable u using the following equations. Here variable u is considered because the movement of the beam is in the x direction. So from moment curvature relationship, we have my dash equal to eiy into minus d square u by dz square. From slope curvature relationship, d theta y dash divided by dz equal to minus d square u by dz square. Here both the terms contain negative because the origin is in the direction opposite to the y-axis. Here both the equations contain the negative term because the origin is in the direction opposite to the direction of the axis. So d theta y dash is equal to minus d square u by dz square into dz. Substituting the terms in dw external is equal to dw external is equal to half into my dash into d theta y dash. So we have half into eiy into minus d square u by dz square into minus d square u by dz square into dz. So we have half into eiy into d square u by dz square the whole square into dz. So integrating over the length z between limits 0 to L, we have 0 to L dw external is equal to 0 to L half into EIY into d square u by dz square the whole square into dz. Now let us look at strain energy due to twisting, which is u sub bz dash. So the increment of external work dw external performed as a result of twisting is given as half into mz dash into d gamma. Let us rewrite the term mz dash with the variable gamma using the following equations. From the generic equation for torsion, we have mz dash equal to gj into d gamma by dz minus eiw into d cube gamma by dz cube. The second term, which contains warping, is equal to 0 because for non-circular cross sections, here IW is taken as 0 because IW is negligible for narrow rectangular cross sections. So this becomes mz dash equal to gj into d gamma by dz. Rewriting d gamma as follows, which is d gamma by dz equal to d gamma by dz, which can also be written as d gamma equal to d gamma by dz into dz. So substituting the terms in dw external is equal to dw external equal to half into mz dash into d gamma, which becomes half into gj into d gamma by dz into d gamma by dz into dz. So that gives rise to the equation half into gj into d gamma by dz the whole square into dz. Now integrating over the length z between limits 0 to L, we have 0 to L dw external is equal to 0 to L half into gj into d gamma by dz the whole square into dz. This equation is not applicable for non-uniform torsion. This equation is not applicable for non-uniform torsion because this equation is not applicable for non-uniform torsion because IW has been taken as 0. Now, the strain energy due to twisting for I section is given as U sub Bz dash. So, as discussed in torsion for non-circular sections, I sections undergo warping which induces lateral bending of flanges. Further, when warping deformation is restrained, as you can see from the right hand side of the picture, the resistance to applied torque is obtained from the lateral bending of the flanges. Hence, the strain energy due to lateral bending of both the flanges can be obtained from B by replacing Iy equal to Iyf and U equal to U sub F. Basically, we are only looking at the flanges. That's why the term F has been given in both the moment of inertia as well as the displacement. So 0 to L dw ext is equal to 0 to L half into Eiy into d square u by dz square the whole square, which is the equation for B. Now we substitute the above terms. So ubz dash equal to 0 to L half into Eiyf into d square u sub f divided by dz square the whole square into dz. Now let us find out the relationship between the twist of the cross section gamma and the lateral displacement of the flanges u sub f. As you can see from here, tan gamma equal to opposite by adjacent, which is u sub f divided by h by 2. Now for small values of gamma, tan gamma equal to gamma, which means that gamma equal to u sub f divided by h by 2, which means that u sub f equal to h by 2 into gamma. Now we can replace u sub f with h by 2 into gamma. So we have u sub bz dash equal to 0 to L half into Eiyf into d square h by 2 gamma divided by dz square the whole square. So we get the term Eiyf into h square by 4 into d square gamma by dz square the whole square. We know that warping constant for I section is given as Iw equal to Iyf into h square by 4. This u sub bc dash can be written as 0 to L half into Eiw into d square gamma by dz square the whole square into dz. So let's look at the total potential energy of the beam now. So the total potential energy is given as U equal to UBx dash plus UBy dash plus UBz dash. Now let's substitute the values from A, B, C. So we have this equation as you can see on the slide. Now let's also substitute UBz dash from D to obtain U for an I section. So we have the equation that is shown here, which includes the fourth term as a result of warping. The first term is in-plane bending. The second term, as you can see, is for out-of-plane bending. The third term is for twisting, and the fourth term is for warping. Now, after having completed the strain energy, let's look at the potential energy of the beam due to equal end moments B. So the potential energy due to in-plane bending B1 is given from the figure here. Mx is acting on both sides of the beam. The potential energy due to in-plane bending of the beam is equal to the negative product of the applied moment Mx and the end rotations. So V1 is given as minus of Mx into minus dV by dz at z equal to L plus Mx into dV by dz at z equal to 0. So now when we take the minus sign inside, we have mx into dv by dz at z equal to L minus mx into dv by dz at z equal to 0. So this can be written as lower limit and upper limit, which gives rise to the equation v1 equal to mx into dv by dz at z equal to 0 and z equal to L. Now let's look at the potential energy due to lateral bending and twisting, which we call it as V sub 2. So figure A indicates the end rotations due to lateral bending. There is more rotation at the top, which is delta top, and there is lesser rotation at the bottom, delta bottom, which happens on both sides of the beam. The angle it makes is alpha given on the left side as well as the right side due to the applied moment mx. Now as shown in the figure, the buckling causes the ends of the longitudinal fibers in the beam to approach one another. If the deformation consisted only of lateral bending, the ends of every fiber in the beam would move towards one another the same distance. However, the lateral bending is accompanied by twisting, which you can see that there is a U top as well as U bottom. There is lateral movement out of plane at the top and there is also lateral movement out of plane at the bottom. This means that the ends of the upper fibers therefore approach one another at a greater distance than do the ends of the lower fibers. This gives rise to the rotation alpha of the end cross sections of the member. Let the movement of the uppermost fiber at each end of the beam be given as delta top and the corresponding movement of the lowermost fiber be given as delta bottom. The rotation of each cross section alpha is defined as alpha equal to delta top minus delta bottom divided by h. The potential energy due to lateral bending and twisting is equal to the negative product of the applied moments mx and the rotation of the end cross sections alpha, which means that V2 equal to minus 2 mx into alpha. So now we have delta top and delta bottom are axial shortening due to bending. So now before we go into the beams, let us look at axial shortening due to bending in columns. So when we apply a load P, there is an axial shortening that takes place, which means that there will be a reduction in the length L and there is a bent curvature which is S. So when we apply the load P, there is an axial shortening. So there is a reduction in the length L, but the original configuration now deforms into S, which is more like an arc length. So upon application of axial load, the column undergoes transverse bending. Delta B is the distance by which the ends of the member approach one another as a result of transverse bending. From figure, we can observe that delta B is equal to the difference between the arc length S and the chord length L, which is delta B equal to S minus L. From Pythagoras theorem, the length of the differential element of arc ds is given as ds equal to dz square plus dx square the whole power half, which can again be simplified as 1 plus dx by dz the whole square power half into dz. Upon integrating the left side of the equation from 0 to s and the right side of the equation from 0 to L, we have 0 to s ds equal to 0 to L 1 plus dx by dz the whole square power half into dz. So we have s equal to 0 to L 1 plus half into dx by dz the whole square into dz. Now s is given as L plus 0 to L half into dx by dz the whole square into dz. Now delta B equal to s minus L. So s minus L is given as 0 to L half into dx by dz the whole square into dz. Now substituting delta B equal to s minus L, we have delta B equal to half into 0 to L dx by dz the whole square into dz. Now this is only for columns, but however in beams an equal amount of axial shortening is observed from both ends due to bending. So now we need to consider that there is movement in both the directions, both at the top as well as at the bottom. So the delta B can be split as delta B by 2 and it can be at the top, which is delta top, and also at the bottom, delta bottom. So at delta top, we have delta B by 2 equal to half into 0 to L du top divided by dz the whole square. And delta bottom equal to delta B by 2 equal to 1 by 4 into 0 to L du bottom divided by dz the whole square into dz. Now, how do we find out delta top and delta bottom? So, the delta top and delta bottom is given from the equation on the right hand side. So, u top equal to u plus gamma h by 2 based on geometry. So, substituting u top equal to u plus gamma h by 2 from figure B on the right hand side, we have delta top equal to 1 by 4 into 0 to L d by dz into u plus gamma h by 2 the whole square into dz. Which we can further simplify as you can see from the right side. and then we can expand the expression using a plus b the whole square equal to a square plus b square plus 2ab. So now we have delta top equal to 1 by 4 into 0 to L du by dz the whole square plus h square by 4 into d gamma by dz the whole square plus 2 into du by dz into h by 2 into d gamma by dz bracket close into dz. Similarly, for delta bottom, we have delta u bottom is given as u minus gamma h by 2, which is also from figure B. So when we substitute that, we do the same expansion. Here it is a minus b the whole square equal to a square plus b square minus 2ab. We get delta bottom equal to 1 by 4 into 0 to L du by dz the whole square plus h square by 4 into d gamma by dz the whole square minus 2 into du by dz into h by 2 into d gamma by dz bracket close into dz. Now substituting the terms in alpha equal to delta top minus delta bottom by h, we have this equation. It's a long equation that you can see in the slide, but we can simplify this equation by cancelling the terms. So the ones that are left over are given as alpha equal to 1 by h into 0 to L du by dz into h by 4 into d gamma by dz into dz plus 0 to L du by dz into h by 4 into d gamma by dz into dz. Now we can take h common and we can eliminate h, and we can add 1 by 4 and 1 by 4. So it becomes alpha equal to half into 0 to L du by dz into d gamma by dz into dz. Now let's substitute that into the equation v2 equal to minus 2 mx into alpha. Now v2 equal to minus 2 mx into half into 0 to L du by dz into d gamma by dz into dz. This can again be simplified further because the half and 2 gets cancelled. So we have v2 equal to minus mx into 0 to L du by dz into d gamma by dz into dz. So we have the potential energy due to in-plane bending V1, and we also have the potential energy due to lateral bending and twisting V2. So substituting V equal to V1 plus V2, we have this equation as shown here. Now substituting the values of U, V for total potential energy, pi of the beam equal to pi equal to U plus V, we have a lengthy equation as shown here. Again, this equation can be further reduced because the dV by dz is very small. The in-plane deformations, bending deformations are very small when a beam is subjected to lateral torsional buckling. Hence, V equal to 0. Therefore, dV by dz is equal to 0. So, we get this equation as shown below. This is for a rectangular section with n moment of mx. So, now what we see here is a generic equation for total potential energy of the beam with an equal end moment of magnitude mx. Now we have the generic equation for total potential energy of the beam with an equal end moment of magnitude mx. The only difference between the previous equation and this equation is that there is a term for strainage due to warping, as you can see here, 0 to L half into EIW into d square gamma by dz square the whole square into dz. Now let us solve this for an equally applied end moments of equal magnitude for an I cross section. So we establish the total potential energy pi of the system. So consider XYZ to be the global coordinate system in undeformed configuration of beam. Upon application of external moment m0 at shear center, the beam undergoes lateral torsional buckling as shown in the figure. On the right hand side, you can see that there is movement in the y direction, there is movement in the u direction, and there is also movement in the twisting direction, which is gamma sub m. Now, each cross-section in deformed configuration can be defined using three displacement components u, v and gamma with x dash, y dash and z dash as the local coordinate system. The ends of the beam are assumed to be restrained against twist, which is gamma equals 0, and free to warp, which is gamma double dash is equal to 0. These two conditions will help in arriving at the constant for the differential equations based on the boundary conditions. Now, establishing the total potential energy, pi of the system is given. Now, establishing the total potential energy, pi of the beam, is given by this equation below. Here, we can also omit the term V, which is very much less than U and gamma. So now, let us omit the first term because V is very much less than U and gamma. So, the equation on the right hand side is much more simplified now. Now, let us choose the deflection functions for U and gamma. So, the deflection function for U equal to A sin pi z by L and gamma equal to B sin pi z by L, and both of them leads to approximate solutions. And let us check if these approximations satisfy the boundary conditions. So, the boundary conditions as we described are assuming ends of the members are laterally restrained, which is U equal to 0, free to bend about minor axis, which is u double dash is equal to 0, restrained against twist, which is gamma equal to 0, and free to warp, which is gamma double dash is equal to 0. Now the first derivative u dash is given as u dash equal to a pi by l into cos pi z by l, and u double dash is given as minus a into pi square by l square into sin pi z by l. Gamma dash is given as b pi by l into cos pi z by l, and gamma double dash is given as minus b into pi square by l square into sin pi z by l. So these are the derivatives. So when we apply the boundary conditions, u equal to a sin pi z by l, at u at z equal to 0 becomes a into sin 0, which is 0, and u at z equal to l, again a sin pi, which is also 0. Similarly, u double dash, when we apply at z equal to 0, sin 0 becomes 0. So u double dash at z equal to 0 is 0. Similarly, u double dash at z equal to l, again sin pi l by l, which is sin pi, which also becomes 0. Now let's look at the boundary condition C, which is gamma equal to b sin pi z by l. So we have gamma at z equal to 0 is also 0 because sin 0 is 0. Similarly, gamma at z equal to l is also 0. And gamma double dash here at z equal to 0 is also 0. And gamma double dash at z equal to l is also 0 because sin pi is 0. Now we can understand that the deflection function and the rotation function that we have given here satisfies all the boundary conditions, which is A, B, C, and D. Now let us substitute these approximations into total potential energy equation of the beam pi. So when we do so, we have this equation here. We have 4 integrals, 1, 2, 3, and 4. So we can simplify this by solving one by one. So let us focus integral 1. Before we do so, let us use the derivatives used in the problem, which is u equal to a sin pi z by l, du by dz equal to a pi by l into cos pi z by l, d square u by dz square equal to minus a into pi square by l square into sin pi z by l. Similarly, gamma equal to b sin pi z by l, d gamma by dz equal to b pi by l into cos pi z by l, d square gamma by dz square is equal to minus b into pi square by l square into sin pi z by l. So let us solve part 1, which is 0 to L 1 by 2 into eiy into d square u by dz square the whole square into dz. So when we do so and we substitute the values here, we get the constant into 0 to L into sin square pi z by L into dz. We have here a square into pi power 4 into eiy by 2L power 4 into 0 to L 1 minus cos 2 pi z by L divided by 2 into dz. So we can solve this using the UV rule, and finally we get the value a square into pi power 4 into eiy into L divided by 4L power 4. So we have a square into pi power 4 eiy divided by 4L cube. This is the solution for the first part, which is number 1. Similarly, we can solve for number 2. Here again, we can expand it. So we can again solve this one, and we get the equation half into gj into b square pi square by L square into 0 to L cos square pi z by L into dz. This 0 to L cos square pi z by L actually becomes L by 2. So when we do all the derivations, we will get that it is actually equal to L by 2. So we have the value 1 by 4 into gj into b square into pi square by L. Now we can solve this problem by substituting 0 to L sin square pi z by L as L by 2. So when we do so, we have eiw into b square pi power 4 by 4L cube. Solution 4 is also very simple. We do the same thing here, and when we do so, we can say that 0 to L cos square pi z by L into dz is equal to L by 2. When we substitute it, we get the value minus m naught into ab into pi square by 2L. So now we have 1, 2, 3, and 4, which can be substituted in the pi equation. So the total potential energy of the beam is given here. So using the principle of stationary total potential energy for equilibrium, the total potential energy of the system pi should be equal to 0, which means that del pi is equal to 0. So the critical moment is reached when the neutral equilibrium is possible. The requirement for neutral equilibrium is that the partial derivative of pi with respect to a and b should vanish. So we differentiate partially with respect to a. We have del pi by del a is given here. When we substitute that, we have a very simplified equation here, which is pi power 4 into eiy divided by 2L cube into a minus m naught critical pi square by 2L into b is equal to 0, which becomes equation 5. We do the similar exercise now applying partial derivative with respect to B. When we do so, we simplify this further and we get one more equation, which is 1 by 2 into Gj into pi square by L into EIW into pi power 4 divided by 2L cube into D minus M naught critical into pi square by 2L into A is equal to 0, which becomes equation 6. Now this 5 and 6 can be in the form of a matrix A by B. So we have this in the form of a matrix AB. So we have this equation represented in the form of a matrix. So for a non-trivial solution, the determinant of the matrix should be equal to 0. So when we do so, we can expand this equation and we can see that when we simplify this equation further, we get the second term here. We can expand these equations and simplify these equations further. As you can see, step by step, we are simplifying this equation. Take the terms 4 on both sides of the equation. Again, we get another simplified equation. We apply square root on both sides. And when we do so, we had M naught critical into pi square by L on the right hand side. Again, we can simplify this further by taking pi square by L outside. We can take the pi square by L on both sides getting cancelled. This equation can be further simplified by multiplying and dividing with root of EIY by L on the LHS. So when we simplify this further, we have M naught critical equal to EIY by L into root of Gj pi square by EIY plus IW into pi power 4 divided by IY into L square. Again, we multiply and divide with root of pi power 4 by L square on the LHS. We further simplify this equation, basically algebraic manipulation. When we do so, we get M naught critical equal to pi square EIY by L square into root of IW by IY plus Gj L square by pi square EIY, which is exactly the same as the equation that is given in Annexure E, page 128 of IS 800. What we can observe here is that the energy method leads to the same equation that we derived using differential equation method. The reason that we re-derived this one using energy method is to simply prove the fact that energy method and the differential equations are one and the same. One advantage of energy method is that it can also be used to solve problems where the loading conditions are different. So going forward, we will solve problems whose loading is not uniform on both sides, that is not N naught on both sides, but it will have different moments, which we will see in the next class. Thank you very much.